Hello, this is a video corresponding to chapter 4 of the text, section 4.6 on indirect proof. And that's this whole video is just going to be introducing indirect proof, going through some examples, and then some rules for indirect proof that correspond to the rules for conditional proof that we saw in chapter 3. So what is indirect proof? It's similar to conditional proof in that you're going to have a subproof. You're going to start a subproof, you're going to make an assumption, you're going to derive something, then you're going to close that subproof off. And then once the subproof is closed, there's a specific thing that you have to write at the end of the subproof that is what you were trying to derive to begin with. The difference is that where conditional proof, you could only directly derive a conditional. You can use indirect proof to directly derive any statement. And by any statement, I mean any form of statement. So it could be an atomic statement, it could be a conjunction, it could be a conditional, it could be a disjunction, whatever. Okay, it doesn't have to be a conditional. So whatever that statement is, let's just call it phi. This is the statement you want to derive. Now, of course, if you could figure out how to derive it some other way, just using the rules, you'd do that. Okay, but suppose it's not immediately obvious to you how to do it. Or maybe you're just lazy and you're pretty confident with indirect proof. So you're just going to do indirect proof. How does that work? Well, it works in the following way. Strategically, or sort of in thinking of it in terms of overall strategy, it works by, instead of establishing phi, there should be establish, typo there, you show that phi is true, or you derive phi indirectly by showing that not phi must be false. Of course, if not phi has to be false, then phi is true. So that's why it's called indirect proof. You're not directly establishing phi as true, you're directly establishing not phi as false, and then concluding that phi must be true. Well, how do you do that? Well, you do that by assuming phi, showing that if you assume phi, you can derive something you know is false. And remember, the rules are truth preserving. So if you can derive something false, that means that something that you are applying the rules to can't be true. Because if you were applying the rules to only true things, you'd never be able to derive something false. So if you can derive something false, that means something you were using the rules on has to be false. And the only culprit is the assumption you made, not phi. That's the basic idea. Before I get into the details of that, let me just point out that this basic idea is something that people kind of use in everyday life. Okay, so suppose you are Ashley, right? That's who you are, and you've got a roommate named Marta, and you think Marta stole your cupcake and ate your cupcake, and you're kind of pissed off at Marta. So Ashley wants to establish this is phi. Marta ate the cupcake. And Marta's denying this, but Ashley wants to establish Marta ate the cupcake. Well, here's one way she could do it. She assumes the opposite of what she wants to derive, or what she wants to establish. Well, she's trying to establish Marta ate the cupcake. So she, just for the sake of argument, says, okay, let's assume Marta didn't eat the cupcake. That's the opposite of what she wants, right? She wants Marta ate the cupcake, but she's going to just assume, for the sake of argument, that Marta didn't eat the cupcake, okay? Now what follows from that? Well, here's how she reads. Well, if she didn't eat the cupcake, then there's no cupcake. There shouldn't be a cupcake wrapper in Marta's room, right? That would follow. If Marta didn't eat a cupcake, then there shouldn't be an empty cupcake wrapper in Marta's room. But look, right there in the waste paper basket, there is a cupcake wrapper in Marta's room, right? So you could establish this contradiction between, in this case, there is no cupcake wrapper in Marta's room, and there is a cupcake wrapper. Now, there's two ways to look at it. One is, well, we know at least one of these has to be false. Another way to look at it is this is a conjunction between C and not C, which is a contradiction, which has to be false. But any way you slice it, something that we know is false has been derived by starting with the assumption that Marta didn't eat the cupcake. Well, since this assumption led to a contradiction, then we have to reject this assumption. So Marta did eat the cupcake. Okay. That's kind of an intuitive way this might play out. In more detail, the basic idea is you want to prove phi is true, or more accurately, you want to show that phi follows from the premises that you've already got. But I'm just going to sort of be a little bit not completely technically correct in my way I describe this, just because it's a lot easier to talk about it in terms of truth. But so the basic idea is you want to prove that phi is true, not by deriving phi directly, but by showing that if the premises are true, not phi must be false. And of course, if not phi must be false, then phi is true. So at that point, when you decide you want phi, you add an assumption consisting of not phi. So this is like your assumption with conditional proof, where you assume the antecedent of the conditional want. Now you're using indirect proof. So what you do is you want phi, your assumption is going to be not phi, the opposite of what you really want. Then you proceed using the rules. Just like with conditional proof, you made an assumption and then you're going to continue the rules. Just like with conditional proof, there's a specific thing you're looking for now. With conditional proof, you're going to use the rules to try to derive the consequent of the conditional you wanted. Now you're going to continue to use the rules, but your goal is to derive a contradiction, an explicit contradiction. Okay? What is an explicit contradiction? It's any statement conjoined to the negation of that same statement. So P and not P. Z and X and not Z and X. Okay? We'll see examples of that coming up. But if you derive an explicit contradiction, remember, we know contradictions are always false. And we also know that the rules are truth preserving. So if the rules are applied to only true statements, they will produce only true statements. But we produce something false, right? A contradiction is false. So something we were applying the rules to can't have been true. And the only culprit is the assumption that we threw up there. We're not questioning the premises, but we did just throw that assumption up there. That is then the thing that has to be false. Okay? And because not phi has to be false, phi must be true. So after you have derived your contradiction, you close your subproof with a line, from the bottom of the contradiction back up to your initial assumption. And then on the next line, you write the negation of your initial assumption. Your initial assumption was not phi, so you write phi, which is what you wanted. You wanted phi, which is why you made your assumption not phi. By the way, I want to point something out that's kind of cool. About 10 years ago, there was a student in Phil 10 who was a climber who was heading out to Red Rock to do some climbing on the weekend before a midterm, before a quiz, and was studying while I guess one of his friends was driving. And they got out there, and I'm not a climber myself, but apparently if you're the first person to do a particular climb, you get to name it. And so he named this particular route Indirect Proof, because he was just studying a lot of indirect proof. So it's pretty cool. 2009. Okay, so I guess that was about 7 years ago he did that. Okay, let's see some examples. This is a really easy proof to do, but I'm just going to do indirect proof just to illustrate how it works. So I'm trying to derive not A. I could try to do it using the inference and replacement rules, but I'm going to do indirect proof. What I'm trying to get is not A, so I'm going to assume the opposite. I'm going to assume A. And that's my assumption for indirect proof, AIP. I'm going to do just like with conditional proof. I'm going to indent and have a little arrow here so that anyone looking at my proof can just very easily visually see where my subproof is. Now my goal is just to get an explicit contradiction. And I want to emphasize this. And every time, even though I emphasize it, people keep asking me questions. Well, does it have to be like this? An explicit contradiction is any statement conjoined to the negation of that same statement. Now the statement could be atomic, it could be compound, maybe it's your AIP, maybe it's not your AIP, it doesn't matter. As long as it's a statement conjoined to the negation of that same statement, it's an explicit contradiction. Okay, so that's what we're going for. And you can see it's going to be really easy here. I've got A, so I can get B by modus ponens. I've got B, so I can get not B by modus ponens on 2 and 4. And if I conjoin these, look, I've got a statement conjoined to the negation of that same statement, B and not B. That's an explicit contradiction. So I can end right there. So I'm going to draw my little line from the bottom up to here, closing my subproof. The next line has to be the negation of my AIP, assumption for indirect proof. That was A, so this has to be not A, which is what I wanted because that's the conclusion of the proof. And the justification is lines 3 through 6, indirect proof. Okay? Let's do another one. Now, if you look at this strategically, there's a lot of ways now that you could potentially do this proof. Okay, so let's walk through a couple. One is you could just use the rules. I could just say, okay, I've got inference and replacement rules. I'm just going to crank on these like a madman and eventually get this. And that could potentially work. I think it'd take a little while. Another thing you could do is you could use conditional proof. You say, how could you use conditional proof? It's not a conditional. Here's how. I don't know how many lines it would take to do this, but let's just call that number n. Maybe n is 10, so maybe this is line 10. Whatever, this is the last line of the proof, m or k. So if I can get this on the last line, I'm done. Well, how could I get this on the last line? Well, if I could get if not m, then k, this conditional, then I can just do conditional exchange. So this is line n minus 1. So if this is 10, this would be 9, let's say. If I could get this, I just do conditional exchange to get that. Okay? Oh, well now this is a conditional. I could use conditional proof to get this conditional. Right? Assume this antecedent, derive that consequent. Right? So I would assume not m, derive k. Okay, so start a conditional proof on line 3, not m, assumption for conditional proof. When I get to k, close it off. Next line has to be a conditional whose antecedent was my ACP, whose consequent was the last line. So I could get this conditional by using conditional proof, and then once I have it, turn it into this disjunction by conditional exchange. So this is strategically just one way I could look at this and say, this is one way I could do this proof. I could just do a conditional proof to derive this, and then turn this into that. Okay? Here's another way you could do it. I want this. I want to derive m or k. Another way I could do it is if I could get m by itself, I could go m or k by disjunction introduction. Same thing, if I could derive k by itself, I could get m or k by disjunction introduction. Okay, now notice before I continue with this, I want to say something. This strategy, this is the conclusion. I'm going to try to get that by just getting one of the disjuncts and then disjoining the other disjunct. It's a little bit dangerous in the following way. This proof, unless, on a quiz I make a typo or something or there's a mistake, all of the proofs you're going to get are valid, which means that whatever the conclusion is, that does in fact follow from these premises. Okay? Just because m or k follows from the premises doesn't mean that either disjunct by itself necessarily follows. Maybe it does, maybe it doesn't, right? Maybe M actually also follows by itself, but maybe it doesn't. So if I adopt a strategy where I say, oh, okay, well, I'm going to try to get M or K by first deriving M and then getting M or K, that's only going to work if M also follows, not just M or K, but M by itself follows. And like I said, maybe it does, maybe it doesn't. So I might try this strategy, and after a while, if I can't derive M, I might have to rethink it. Okay, but I still might roll the dice and just say, okay, I'm going to give it a shot. So this is what I just said, another typo here, the premises. This will only work if M by itself follows from the premises, and in this case it might not. Just because the premises jointly imply M or K doesn't necessarily mean that they will jointly imply M. But I'm going to go ahead and roll the dice and assume, or at least try it and see if they do. How could I get M? Well, I could get it by just cranking it out with the rules, or I could use indirect proof. I'm trying to get M, I could assume not M. That would be my assumption for indirect proof, and then derive an explicit contradiction. Now, I don't know what form that's going to take. I know it's going to be some statement conjoined to the negation of that same statement, but I don't know what statement that is yet. So I'm just going to put in kind of like a filler here, some explicit contradiction. And then derive M. Assume not M, contradiction, M, and then DI to get M or K. Now, the reason I went through this is just to illustrate that now that you've got a lot of tools, you've got these rules, you've got conditional proof, you've got indirect proof, there's a lot of ways you can approach any proof that you're given. And so one thing you can do is just look and sort of think strategically, because notice this strategy here, this sets up the whole structure of my proof. I know what the last 3 lines are going to be. That's the last line, that's the second to last line is M. The third to last line is going to be me closing a subproof off with some explicit contradiction. Line 3 is going to be this. The only thing that's left that I don't know, that hasn't been established by my strategy, is just these middle steps. And that's actually a lot easier, as we'll see. So I'm going to go ahead and do that. I'm going to assume not M, because I want M, and then get M or K. So assume not M, assumption for indirect proof. And now I'm just going to try to get a contradiction. One thing that makes indirect proof easy is that if the thing you're trying to derive really does follow from the premises, then the negation of that will be inconsistent with the premises. And once you're working with inconsistent statements, it's usually pretty easy to derive a contradiction. Even if you just use the, apply some rules and see what happens, a contradiction will usually fall in your lap pretty quickly. So what rules can I apply here? Well, look, this is a conditional, this is the antecedent. If I had this antecedent, I could get that by modus ponens. How could I get not M or P? Well, I've got not M. So I could go not M or P by DI on line 3. Now this is the antecedent of that, so I can get K and not L by modus ponens on 4 and 1. And if you look at 2 and 5, there's just a lot of contradictions here. First off, if you just do De Morgan's on this, you will get not K or L. You'll just get the negation of that. So I could just do De Morgan's on this, and it would just be the negation of that, and then conjoin them, and that's my explicit contradiction. That's one way to go. Or I could simplify these off and get a contradiction from the atomic statements. That's the way I'm going to do it. So I'm going to simplify off K and L from line 5. And then I'm going to do disjunctive syllogism on 7 and 2. Disjunction, I have the negation of the second disjunct. I've got not L, so I can derive K, not K, by ds. And then look, K and not K. So I've got a statement conjoined to the negation of that same statement. So there's an explicit contradiction. I'm going to close the subproof. Next line has to be the negation of my AIP, so M. And then I'm going to use DI to get M or K. And I got a little bit lucky because M really does follow from these premises, and so I was able to derive it. Let's do another one. Again, strategically, if you look at this, a lot of ways you could go. One, you could just try to use the rules, inference and replacement rules by themselves. This is a little tricky, especially if you're only using the rules, the regular rules, not the optional material, because I think if you try to do this, the rule of exportation comes in really handy. In fact, it might be necessary to use that if you're not doing any subproofs. But let's do a subproof. And there's two ways we could go about it with subproofs. Actually, there's a lot more than two ways, but here's the two obvious ways. We could do conditional proof. This is a conditional. I could assume D, try to derive C. And if you look at this, you can see it's really easy, right? If you assume D, then you can get P and I, simplify I, then I or S by DI on I, then C by modus ponens. So that's actually pretty fast. The other thing you could do is use indirect proof. I'm just going to assume the negation of this and derive a contradiction. So that's what I'm going to do. I'm going to assume the negation of what I want. What I want is if D then C. So I'm going to assume not if D then C, and then just derive a contradiction. Now I can't really work with a negated conditional, but if I turn this conditional into a disjunction by CE, now I can work with this. I can do De Morgan's on that to get D and not C. Then I can simplify D off by itself. In fact, I'm also going to simplify not C. Now that I've got D, that's the antecedent of this, so I can get P and I. And now I can simplify I. Why? Because now I can go I or S by DI on line 9. Now this is this antecedent, so I can get C by modus ponens on 1 and 10. And now look, I've got C and not C. C, not C. So I'm just going to conjoin those, C and not C. There's my explicit contradiction. I'm closing my subproof off. Next line has to be the opposite of the thing that led to that. So if D, then C. Okay. Now, you've seen some examples of indirect proof. Let's go through the rules for indirect proof, which are very similar to the rules for conditional proof from Chapter 3. First, once you know what you want, you're going to start a subproof. You're going to indent the line, right, with a little arrow to your assumption, and you're going to justify the assumption with AIP, assumption for indirect proof. Second, indirect proof ends only when an explicit contradiction is derived. So this is different from conditional proof. Remember with conditional proof, Rule 2 was you can end a conditional proof anytime you want to. Okay? No matter when, where you are in your subproof, you could always just decide to end it right there, and you're not going to lose any points for doing it wrong. Whereas if you end an indirect proof on anything other than an explicit contradiction, you're going to lose some points. Okay? That last line of your subproof has to be an explicit contradiction. Once you've done that, you mark off your indirect proof. You sort of draw the line from the bottom of the explicit contradiction back up to your arrow, which is sometimes called, you're closing the subproof, sometimes called discharging your assumption. The next line, after you've closed the subproof, can only be the negation of your AIP. That's it. And that's good. That's what you wanted. You made the AIP that you did because you wanted the negation of it. So all subproofs have to be closed before the proof can end. This is just like with conditional proof. Same thing applied. So for example, this is the proof we just did. Suppose you got up here to line 6. You're looking at this and you're saying, oh, hey, look, I've got K. I'm trying to derive M or K. So I can just do DI on line 6 and now I'm done. Well, you're not done, and you would get points, a lot of points taken off of this because you're trying to end a proof before you've closed your indirect proof. So I'm going to put a big red X there. You can't do that. Okay, so all subproofs have to be closed before your proof can end. Last rule, once a subproof has been closed, no individual lines in it can be used or cited. You can't cite those lines anymore. So for example, you might have done this proof, boom, boom, M, and you're thinking, how can I get M or K? Well, of course, obviously you can get M or K by doing DI on line 10. But suppose you didn't see that. Suppose instead you saw this K here, and you said, oh, I know. I can get M or K by doing DI on line 6. No, because here, after the subproof has been closed, you're trying to cite a line that's in that closed subproof, and you can't do that. Okay, once you've closed the subproof, this is all quarantined. Okay, that is it for indirect proof. What we're going to do next time, in the next video, is basically just work through a bunch of examples of proofs that use everything we've seen so far. Conditional proof, indirect proof, all of the inference rules, all of the replacement rules.